So we've got two computer science students graduate from Heritage and both come to you to manage their investments. Graduate A begins saving $200 at the end of each month immediately after graduating in an account that earns 6% interest, compounded monthly, and continues to pay into that account for 15 years. After 15 years, Graduate A decides to stop contributing to the fund, but leaves the money in the account for an additional 25 years. And Graduate B waits 10 years to begin investing in an account that earns 6% compounded monthly. How much would each monthly payment made at the end of each month need to be in order to have the same amount in the account as Graduate A after 40 years? And which graduate gets a better return on their investment and why? And we need to describe why the investor who ended up with more money did. What characteristics of the investment caused that to happen? So we've got Graduate A set up here. This person is putting away $200 per month at 6% interest for 15 years. So 0.06, it's monthly, doing this for 15 years. And then after 15 years, he decides to stop. So that money is going to turn into a lump sum and continue to grow by compound interest. So we've got our 0.06 over 12. And let's see what that comes out to be. 0.005. And MT is 12 times 15, so 180. So let's go ahead and swing that into our formula here. This is future value of an annuity because we have a fund that is growing, hopefully. And the I Schlegel is 0.005. N is 180. And so there we go. I got to get my formula. Again, future value of ordinary annuity or future value of annuity because the amount of money we're contributing to this account and hopefully the size of the account is growing. And there we go. So we end up with $58,163 and 74 cents. So that amount of money is going to be there after 15 years, and then he stops contributing to the account, or she stops contributing to the account, but leaves the money in the fund for another 25 years. So 40 years total that this money will be in there. So it's quite a lot of money that this person has over this period of time. So just a little bit of quick math to figure out how much money they grew here. So $200 a month for 15 years. They only put in 36,000. It's already grown to 58,000, which is pretty awesome. They're going to be smart and let the money sit there and continue growing. And so this is going to be compound interest. So it is a lump sum that is sitting there growing now because the recurring payments have stopped. So it's kind of a funky looking I there. 1 plus I to the power of n. And so the amount that's in the account is $58,163.74. The interest rate is still going to be 6%. Still compounded monthly. It's left in there for 25 years. And so I is R over M. Going to be 0.005. Just going to double check that, make sure I did that correctly on my calculator in the first place. I did. Okay. So N is MT. 12 times 25. We get 300. Something tells me that the value of this money is going to explode. So we are going to have S is equal to $58,163.74 times 1 plus 0.005 to the power of 300. So back here with our compound interest formula this time. So S equals 58,163.74 times 1 plus 0.005 to the power of 300. And yep, it does explode. So 259,699 bucks. $259,699.34. So you can see over that 25 years of just sitting there that 58,000 grew like crazy to 259,000. That's pretty awesome. Remember that time is fertilizer for money. And so after 40 years, grad A. Let's remember how much this person put in. Everyone, they put in 200 per month. So again, 200 times 12 times 15 years, they put in $36,000. Grad A invested a total of 36,000 bucks. And ended with $259,699.34. So they made about $220,000 for doing nothing, but just putting some money in the investment. So a return on investment is about, another way to say that is growth, is about 220 grand. That's pretty awesome right there. So now we're looking at graduate B who has waited 10 years to begin investing. That's a bad decision, graduate B, and wants to have the same amount of money in the account that graduate A does. And this person has 40, let's see, so after 40 years, it's going to be, our T is going to be 30, everyone, because we're considering these two people having graduated at the same time and sort of going at this person starting 10 years later than that one. So I'm going to make that more clear in the presentation that you receive, that this it is 40 years after graduation, not after they start investing. So our T for graduate B is going to be 30. And I'm going to change my pages and get this ready to go for graduate B. Okay, so I've already set up my SERMTIN and I filled in that I know we need $259,699.34 in the account. That's how much graduate A ended up with. And graduate B is trying to catch graduate A. Graduate B wants to know, how much do I need to put away monthly in order to make that happen? And that person has 30 years to get it done. It's going to be compounded monthly, and the rate is going to be the same as it was for graduate A, 0.06. So our R over M is 0.06 over 12, so 0.005. And then MT is 12 times 30, so 360. And I have no idea where my iPad went. I'll get it back. So we've got our information in there, everything that we need to know. And this is a future value of an annuity again. But this time we know how much we're shooting for, and we are looking for how much we need to put away monthly to make it happen. So we will have our future value of an annuity formula. So 1 plus I to the n minus 1 over I. And so our S is going to be 259,699.34 equals R times, we don't know what we don't know what R is going to be. That's what the payment's going to be, 1 plus 0.005 to the power of 360 over 0.005. So on to Wolfram we go with our future value of annuity formula. We want to have 259,699.34 in the account. Don't know what the payment's going to be. I is 0.005. N is 360. And so again over here, 0.005. Got to do some division, dividing by 1,004 and 52 cents. And so the payment that this person needs to make every month to catch graduate A would be $258.53. So grad B must invest $258.53 every month for 30 years to catch grad A. Yowzer. So if you remember, grad A only had to invest $200 a month, and they only did it for 15 years. Grad B, because this person started 10 years later, has to invest more money every month, $258, and they've got to do it for 30 years. So we are going to do a little bit of an analysis on why this, who ended up with a better return on their investment. And so we need to come back here for a moment. So let's take a look at the total amount invested by grad A. So the total amount put in the account was $36,000. The return, the ending value was $259, and the return was about $220,000. So we need to figure out how much graduate B invested, what they ended with, and how much they made on the investment. So let's get right to that. So total invested is going to be the $258.53 every month times 12 months times 30 years. And I'm going to move this math up there so that I can keep my statements together down here. All right. And so I get 258.53 times 12 times 30 years. This person has to invest $93,070.80. So total invested is $93,070.80. That's quite a lot more. Total, what did I call the other thing? Total invested. They ended with, so ending value is the same as graduate A. They were able to catch graduate A by doing this. So 259, 699.34. And so the return on the investment, or the growth, either way of saying that, the growth is about $166,000. Not too shabby, but when we compare this to graduate A, the return on the investment for graduate A was $220,000. Graduate B was about $166,000. So grad A had a better return on an investment by about, let's see, 166,000 compared to 220,000 by about 54,000 bucks. So Put simply, graduate A and graduate B ended up with the same amount of money. Graduate A started earlier, and so didn't have to invest as much to get to the same amount. And so again, graduate A and B ended with the same amount, but it cost graduate B $54,000 more dollars to get there. Lesson is invest as early as you can. The end.